title is Existence of Approximately Macroscopically Unique States. Let's welcome.
Thank you. I would like to take this opportunity and privilege to thank all the organizers, not just Professor Yao, but all the students, volunteers from airport to hotel and here. So thank you. This is also a nice place. Yanxifu. It was translated to Swan Lake. And last year I was here too. I didn't see any swan, but they promised that there will be some geese there. And I hope that I can see them this year later on. So I will talk about the existence of approximately macroscopically unique states. I will soon define them. By the way, I will join Shanghai Institute of Mathematics and Interdisciplinary Sciences next month. So in quantum mechanics, macroscopical observables may be represented by self-adjoint operators like T1, T2 to Tn on Hilbert space H. And the commutators are usually related to the uncertainty principle in their measurements, and the small commutators indicate more precise measurements. Let's fix a unit vector as a vector state. The expected value when measuring an observable given by Tj is just a numerical number as in the product with V. More interesting vector states are certainly eigenstates and the vector states given by eigenvectors. The joint expected value associated with the V is n tuple a point in Rn. In his recent book, David Mumford proposed to study near eigenvectors for some set of human observables, which he called approximately macroscopically unique state. So Mumford explained that these states describe a world recognizable to us with no maybe dead, maybe alive cats. For a given vector V, vector state V, variance and the standard deviation of a measurement made by Tj are defined by this square and in the product, and then you take a square root. So the following definition was given by Mumford. Let's say that T1, T2, Tn be a given n tuple self-adjoint bounded operators. And you look at this set called ANU. This is just well, a set of unit vectors. So this maybe I should go back. So the standard deviation is smaller than sigma from j from 1 to n, where sigma is a given torus. So this is like a near eigenvector. So you want this thing to small. If sigma is 0, it is just eigenvalue. So following him, one immediately has the question, that's the question one I will stay here, is the set non-empty when the commutator are sufficiently small? Now, I want to emphasize this you want not only one single operator, but from 1 to n, j from 1 to n, simultaneously. Okay. So in the first International Congress of Basic Science held last year, David Mumford gave the opening plenary lecture titled Consciousness, Robots, and DNA. At the very end of this magnificent lecture, he asked whether there are nearby, with a small tolerance, an n-tuple of commuting self-adjoint operators. So one may project them to a common eigenvector space.
I'm sure that everyone is aware of the GPT and the impact. This talk, however, is not going to go into significant details, which are very extremely intriguing, but really it's going to be about philosophy, physics, and biology, and really no mathematics.
So he said no mathematics at the very beginning, so I sort of, lost. But at the very end,
The question of how to project. So there's a problem with C-star algebra here, which is quite fascinating. You can take the collection of all macroscopic observables, and you can ask the question, what happens when we open our eyes and see the experiment? So certain of these self-adjoint operators are going to be projected into an eigenstate. But what happens if there are cat states all around, and we're continually, through our observations, projecting into eigenstates? So you have the problem, we have a C-star algebra of these macroscopic variables. So we have two alternatives. Can we find, are there operators close to these within those tolerances which commute, and therefore you can project onto a true eigenstate of all of them, or not? So, in other words, a projection operator which results by opening your eyes and seeing the world, and seeing that it's in a definite state. That itself is a non-trivial mathematical problem in the area of C-star algebras. I worried about this a little bit and corresponded with the master, Elaine Kahn, on it, but and it's a difficult question. Okay, that's it.
so that's the end of his talk. It's my talk, not his talk today. So at the end, he suddenly talked about C-star algebras and self-adjoint operators. He consults Alan Kump, not me. But let me reformulate his question. So a version of the question may be formulated as follows. So I will call the question 2. So let epsilon be positive and an integer, positive integer. And when is there a constant delta positive, such that the following statement holds. If H is any separable Hilbert space, and T1, T2, Tn are operators, self-adjoint operator, we normalize it. Say the commutator is small within delta, there exist self-adjoint operators S1, S2 to Sn. such that they actually commute but close to TIs, I from 1 to n. So he want to find nearby self-adjoint operators. They actually commute but close to the original ones. So that was the question he asked. So if you do have these S1, S2, Sn, then you can project into the eigen space, and then you have this A and U. Okay, so this is the second question. So when n equals 2, and H is any finite dimensional Hilbert space, no bound on the dimension, the same problem is known as the von Neumann-Cadison-Harmos problem for almost commuting self-adjoint matrices. For that, you have a formative answer. That is, let epsilon be positive, then you can find delta depends on epsilon only, satisfying the following. For any self-adjoint matrices of any size, say T1, T2, but you normalize them, suppose the commutator is small within delta, then they are indeed self-adjoint matrices S1, S2. They commute, but they're close to the original operators. Just to remind you that before this theorem, Voiculescu showed that the above is false if we replace self-adjoint matrices by unitaries. This is, roughly speaking, if you go very far, you see far away 2 pair of unitaries, you will see a torus. And there is a topological obstacle to have this thing. You cannot replace self-adjoint operator by unitaries. But on the plane, after Voiculescu theorem, you will see on the plane there is no obstacle topologically, and therefore you actually can do it. Okay. Let me state a corollary of this. Well, this is if n is fixed, then you do have a formative answer. You get a small. So this thing is independent of the size.
There's no delta that's independent of that.
Yeah, this delta does not depend on n. Yeah. So therefore, we can state a corollary. So for epsilon positive, you can find a delta such that if T1, T2 are just compact operators, if a commutator is small, then yes, you can find commuting pair of self-adjoint operators. They are close to the original one. If T1, T2 are assumed to be compact. Now, it looks nice, but it's not what the Mumford look at. You want to have on the infinite dimensional Hilbert space, not necessarily compact. Okay. So the previous theorem doesn't apply immediately. You can apply this case, but not in general. So let me give a little bit background again. So in quantum mechanics, one often hears when commutators tend to 0, or this H bar go to 0, we recover the classical system. Indeed, if observables in the system are compact self-adjoint operators, and then the above corollary states that a pair of observables can be approximated by commuting observables, and when the norm of the commutator is small. Unfortunately, the answer to question 2 in general is negative. In other words, even when the commutators tend to 0, It's a little so even when the commutator tends to 0, this system may be very far away from classical system. I tried to explain my colleague in physics. They couldn't find out commutators and almost commuting seems the same thing, but they are not. So let me get into some technical things. So you fix a point in Rn. You define a function theta lambda I eta as a continuous functions from 0 to 1. Roughly speaking, I want 1 at lambda I, and when it's far away, it's just 0. And I want to connect them linearly, so it's continuous function. And then for each t, I define a function as a product of those things. Okay, so it's capital theta, it's Cauchy eta is the function. And let me just maybe show you a picture. So theta function, little theta is just 1 at lambda I, and outside is 0. So you sort of detect this lambda I, okay? And so this theta Cauchy eta is the product of those. You have lambda 1, lambda 2, lambda n. Okay, so take this function. And now suppose A is a unit of C-star algebra, and you take n tuple of self-adjoint elements in this C-star algebra. Let's say the norm is no more than m, and you can define this operator. So it's a product. For let's say that the first effect, if you look at our matrices, you diagonalized, so you have eigenvalues. You perform this lambda, the theta function on these eigenvalues. If it's close, somehow you have a eigenvalue close to lambda 1, then you got a 1, otherwise 0. So you detect those, and you put the product there. Okay. Now, we do not assume A1, AN mutually commute, so this product has a fixed order. Okay. If they actually commute, then, and the Cauchy is in the joint spectrum of A1 to AN, then of course this norm is 1 because you detect the lambda, detected as Cauchy.
Can you put a possible definition of small theta?
Small theta. Yeah, small theta is just dysfunction. So you just try to detect the lambda I. The rest of them is 0. Okay. Eta is a torus. Okay.
So small theta roughly projects onto eigenvalues very close to lambda.
That's right. So you just try to detect if this eigenvalue is there or not, jointly, of course. So if there are commutes, then in the joint spectrum, then of course you detect it. So norm is 1. So just bear with me. I want to have some notation fixed. So you just put some dense points in Rn. Okay. So this has only a finite many points. For a fixed integer n and m, so this gives you a n cube. So you choose a k so that somehow you divide things evenly, and call delta eta those points. Okay, and so it has only finite many points, and the only point here is the eta is half eta dense in this cube. And if we usually choose m equals 1. And so this unit cube. And if you have a small delta, then of course there are more points. Just divide this into small pieces, a cube. So let's go back to a unit OC style algebra, and you still have this n tuple of operators. And recall we define this capital theta. So the purpose of define this is for the following. So we said this set is a union of closed balls. We just look at this value. If this value close to 1, we pick them, otherwise we ignore them. So there are only finite many closed balls. So this set is called eta synthetic spectrum of n tuples. So, which by definition is compact. So let me explain why I want to do this. In general, it's hard to compute a spectrum of operator. I mean, even matrices, you have a larger size, and it's hard to find eigenvalues since you need to find the roots of a polynomial degree higher than 5. And also, the spectrum is notoriously unstable when you do a small perturbation. So this is sort of approximate spectrum. But these are not usual ones, since these are not even commute. Okay, so that's what I call synthetic spectrum. Somehow you approximate, you detect them. So, by the way, so if they are commutes, then this set is large, certainly contain all the joint spectrums there. When you define something, you make sure this is not empty set. So this proposition simply says that yes, when the commutator is small, this thing is a non-empty compact set. When it commutes, certainly we do know that it contains the joint spectrum. If you have an bounded self-adjoint operator, you can define something called essential synthetic spectrum. But it's nothing really new from definition. It's just you look at the Huaxin algebra instead. So the K is the idea of all the compact operators. Okay, you look at the quotient. You look at these n self-joint operator in the quotient. So you're in the C-star algebra. You have n tuple of self-adjoint elements. So you can define eta synthetic spectrum. So this is called essential synthetic spectrum. Okay. So let me state a theorem, theorem A. So let n be an integer epsilon positive, then there is a delta. Depends on n epsilon only, specifying the following. Suppose that H is an infinite dimensional separable Hilbert space, and you have n self-adjoint operators, and we normalize it, and say the commutator is small. Within a delta, and I want two sets, the Hausdorff distance of two sets are small. The first one, X, is the synthetic spectrum of T1, T2, Tn. The second one is the essential synthetic spectrum of T1 to n. If these two sets Hausdorff distance is small, then indeed you can find the self-adjoint operators S1, Sn on H. So they commute and they're close to Tj. So for Mumford question, if I add additional condition, then yes, you can find those commuting self-joint operators nearby So therefore, you can project to the eigen space. You find it's what we call the AMU. No, definitely not. So I will explain what is this second thing is about, and then I will show you. No, it's not the necessary condition. This is a sufficient condition. But let me explain this. So in an infinite dimensional separable Hilbert space, a self-adjoint operator such as Tj may not even have any eigenvalues, but have approximate eigenvalues always. However, if one allows non-normal states of B of H, or let's say the C-star algebra is generated by A and then you add the compacting, then Tj does have eigenstates and eigenvalues in the atomic representation of B of H, or A plus K. In particular, one should consider those states of B of H which vanish on K, the idea of compact operators. If a point C in the unit cube is expected to be a joint eigenvalues, then one may use the test function, this theta C eta, to test it. In order to get this norm large, actually we only need one vector to look at this numerical range and see if this is bigger than, close to 1 or not. You can do this test. One expects this can be repeatedly measured, not just by accident. Say you take any finite many unit vectors and let H1 be the finite dimensional subspace spanned by X1, is X1, and the rest of them. And you look at the orthogonal complement, and you hope this also can be, so this can be also achieved by something outside. So you observe that way. And let's say it persists. Say you observe something here in Benza, you hope it's also can do in the Sims, in New York City, or everywhere else. I mean, you go far away, you can still do it. So that's just say it's a persist. So then we obtain a sequence of xm that are orthogonal to each other. Let's say this still holds for a sequence of xm, not just x1. Note that these unit vector states given by xm has a limit points, so which vanish on k. And you have this theta is large. And so it doesn't affect other things. They may still have unknown eigenvalue outside any finite dimensional space. Let's look at the other way. So let's look at the quotient map. So you modular compact. And say psi is a state of Kroner algebra or Huaxin algebra. Then there's a quantum state. You first pi and then psi, it might better reflect the situation. So you want this thing not only observe locally, you can observe far away on this Kroner algebra. You imagine there is a Kroner boundary somewhere, and that can continue to observe this. So indeed, one may expect that at least for one such quantum state, this thing is still big enough. Measurements given by states of this form may be called outside measurements. And by Geffen-Naiman construction, this quantum state is also given by a vector state, but not on original Hilbert space, but on the Hilbert space from the atomic representation of B of H. In other words, you still have that. So my point is that you should go outside to see that. If whenever this was a x1, you measure this 1, actually close to 1, and you want at least one of the quantum state, still this inequality still holds. If you allow that, then the second condition always satisfied. In that case, it actually equals y. Okay. So this seems to suggest we could put a condition on this macroscopic system. Any local measurements should not be too far off from a outside or a long-term measurement along any orthogonal basis of Hilbert space measurement. Under this condition, when the commutators tend to 0 by theorem A, the quantum system may be approximated by a classical system when the observables actually commute. It looks good condition on it. So let me recall this statement again. It's rather technical now. So you have, given epsilon and n, you have a delta such that for any n self-adjoint operators, we normalize it. So the commutator is small within delta. If these two sets, the essential synthetic spectrum and the syntactic spectrum are somehow close, then you can find S1, Sn, they commute, and they are close to original operators. Okay, so to answer Guoliang's question, let's look at this statement. For n equals 2 case, for epsilon positive, then you can find a delta depends on epsilon only, satisfying the following. Suppose H is an infinite dimensional separable Hilbert space. You have two operators, self-adjoint. You normalize it. If the commutator is small and this Fredholm index of this operator is 0 for any lambda outside essential spectrum, this is true essential spectrum of an operator, then you can find S1, S2, such that they commute and they're close to original operator. And this condition, the Fredholm index equals 0, is necessary. Let me stay slightly different here. So here is a proposition. If you can find commuting ones close to Tj, then for any lambda outside the essential spectrum, this index is 0. So that's necessary. Now it's hard to put such a condition for a macroscopic observables. It's not clear how to do this. So the original, theorem A should tell you that if somehow essential spectrum and the spectrum are the same, then this works. In fact, in that case, that the Fredholm index is automatically 0. Okay. So this is a necessary condition. And in n equal 2, this is also sufficient when the index equals 0. Okay, so let me go back to Mumford's original question. So he asked if you do have A and U. So somehow his second question is very difficult to answer because he thought how to answer, how to get this thing non-empty. You find commuting ones nearby, then you answer this question. But maybe we can answer that question directly without solving his second question. And we know this is difficult to state even. So let's try to do that. So this is the AMU, and he asked whether this thing is non-empty when the commutators are sufficiently small. So here is the theorem. So you fix an integer n and epsilon. Indeed, there is a delta, depends on n epsilon only, satisfy the following. Suppose that H is an infinite dimensional separable Hilbert space, and you have n self-adjoint operators, you normalize it, and say the commutator is small within delta, then for any lambda in the essential spectrum, there exists a V, a unit vector, such that this expected value is close to this lambda I within epsilon. And that means, and this thing is less than epsilon. So AMU do exist whenever this thing is small. Now this statement, the solution of this didn't solve his second question. But he answered the first original one. He really wanted to exist on AMU. So in that way, you do have it. Okay. So that means for any of those values, you can find a V. So let's just give you this. This V give you an AMU. All right. So when you answer this question mathematically, try to add something else to it. So there is no more over part. Actually, not important mathematically, but I will explain this. It says that for the convex hull of synthetic spectrum, you also can find a vector V. So what that means? Okay, well, let's see. So this is the theorem B. So let H be an infinite dimensional separable Hilbert space. We have n self-adjoint operators. Even in a classical system, a system in which the observables, that means self-adjoint operator, commutes, not every n tuple where lambda I in the spectrum Ti can be measured simultaneously. You cannot do that. The requirement is that the lambda has to be in the convex hull, at least. It is well known the spectrum of an operator is difficult to compute. There is a time difference here. Okay. Oh. So,
You could use the keys on the laptop.
yeah, I guess so. Yeah, maybe I should use this. Thank you. So it is well known the spectrum and operator is difficult to compute and unstable for small perturbations. When observables are not commuting, it is even difficult to define what is a joint spectrum. However, as we see, for small epsilon, this synthetic spectrum can be tested, and it's not empty, and when the commutators are small. So this synthetic spectrum, it seems workable replacement. You really want to join the spectrum instead of just any combination of eigenvalues. You want to have things doing at the same time, simultaneously. So let's assume, wait a minute, I'm sorry. Let S1, S2 be AMU states corresponding to joint expected values, lambda and mu, respectively. Then you can do superpositions given by this value. In fact, that for any finite many AMU states, you can do a convex combination, and this gives you a different state. And you will get to the convex combinations. This mixed states measure this value simultaneously. But somehow, if this thing actually in the syntactic spectrum for some small eta, it's not clear whether S should be called a cat state, because see, there's a theta could be an eigenvalue. Let's say this thing is not in the essential and the synthetic spectrum. Then you do have this, what they call the cat state. But it's never Q state, as Q state corresponds to the extreme states. But the question is, could a theta be a joint expected value measured by a vector state simultaneously? The moreover part of theorem B states theta could be approximately measured simultaneously by a vector state, but not AMU. So this is, to me, it's an interesting feature since we do not assume this thing can approximated by commuting operators. Okay. So this is a moreover part. So, you know, a cat could just sleeping, right? Not live or dead. And to me, you can have any other states at the same time. It's not really, to me, it's not so surprised, but yes, there is a sleeping cats, perhaps. But the universe is even more interesting. We could have commutators large in norm, but tend to zero in a different sense. Let's assume H is an infinite dimensional separable Hilbert space with orthonormal base, say UK. Let's say Pm is a projection to the span of first M vectors. And suppose this thing go to 0. In other words, the commutators are compact. Then you can, let's say K, I never really do this, I should denote by K the C star subalgebra of all compact operators, which is an ideal. Then we have the following. Say let H be an infinite dimensional separable Hilbert space, T1, Tn, self-adjoint operators. If the commutators are compact, then for any lambda in the joint spectrum of, you see these operators are commutes in the Cartan algebra. So you have a joint spectrum. If you take any lambda there, then say this pi c is a quotient map. There exists a sequence of H in the Hilbert space itself on the unit sphere.
What's meant by the spectrum of pi c?
So these things, so the commutator is compact, so they are commuting in the Cartan algebra. If you project to, if you look at a pi c, the quotient map, modular k.
I understand, but I don't know what's meant by the spectrum if you're projecting out there.
So you have commuting self-adjoint operators, then it generates a commutative C-star algebra. So Gerfond theorem will tell you have it's isomorphic C of X. This X is defined to be this is a spectrum of these n operators. So in that compact set, you take any lambda, and these lambda can be observed this way. You have a sequence of this. So this thing go to 0, and this thing also go to 0. So this is the sequence of AMUs that should go to 0, not just epsilon. And there is a moreover part which cannot be shown here. So here's the whole statement all the way. There's a moreover part. It said for any elements in the convex whole of the joint spectrum of these operators, which of course in the quotient, these are still values in Rn, and these theta can be approximated this way. In other words, observed by a vector state. So you don't really need this commutator small in compact. That would be fine. Of course, you can do slightly better this way. So you have n self-adjoint operators. Now we do not assume the commutators are compact, but assume they have a small norm in the quotient. Then you can also do it. Now you have to have a synthetic spectrum since they are not commuting. But any lambda here in this set, then it can be observed. Well, let's say you do have a vector v, unit vector, such that these lambda I is close to this expected value. And this is approximated eigenvalue, and this is approximated eigenvector within epsilon. So that's what Mumford originally asked. That is, he worried about too many cat states, and if there is anything at all that you can actually have what he called AMU, approximately macroscopically unique state. So you do have those things. Moreover, any elements in the convex whole can be observed by a vector state, which is not a pure state. So it's not AMU or anything of that. So that's what something called cat states. So it can be all around, as he said. Okay, still have some time. Let me give an example to illustrate at least some phenomenon here. Let's say you just take a shift operator on L2, okay, and you take the real part and the imaginary part, self-adjoint both. So A1, A2 are self-adjoint operators. And actually, I think the norm is 1/2. Yeah, it's 1/2. And it is compact because it is a rank 1 operator. Okay. However, this pair is far away from commuting pairs. Not even a compact perturbation of commuting pairs. So when I say the commutator is compact, doesn't mean that they are compact perturbation of commuting ones. They are not the same. And this is an example that these two operators is not a compact perturbation of commuting ones. So this little delta actually is error there. SS is not a compact perturbation of any unitary. Cannot do that. And nevertheless, by the theorem that we mentioned earlier, for any point on the unit circle, you do have a unit vector, Vk, such that okay, comes up. So you take a sequence of Vn's, this expected value will approach to lambda j. So anything in the unit circle is what the expected values by A and U. And these are approximate unit vector. This is nothing new, and we know this a long time ago. I mean, I'm just giving an example that things are bad in a way, but still good in that respect. And moreover, anything in the unit disk can be observed this way. Now, there are differences, right? They are not the eigenvalues. These theta j is not eigenvalues, approximate eigenvalue in this way. But they are in the numerical range, of course. So cat states to me just in the numerical range. Why this even surprised? I don't quite understand. You know, you take any convex combination that is give you a value like this. So cat states is nothing mysterious to me in that way, at least mathematically. That's what they expected as an order of days. It's hard to find eigenvalues. It's much easier to find numerical values, as we all know. So yes, there are cat states everywhere, and there are sometimes you can get eigenvalues or expected joint eigenvalues that you can have it, and so the answer to Mumford's original question, the first question, is yes, or more or less is yes. But for his suggestion how to solve the problem, that the answer to that question is in general negative. Sometimes you can do it, sometimes you can't, and there is an interesting topological obstacle there. And one may even state a good theory mathematically, but it's not clear. It's interesting for quantum mechanics. So I think I will stop here. And I was told never keep the audience hungry, so it's lunchtime.
Many thanks to Professor Lin's nice talk. Any questions or comments?
Yes.
Is there an easy example that explains the obstruction involving the Fredholm index?
This is actually an example. This Fredholm index is not zero. Yeah. So you cannot approximate this shift over by a unitary.
Well, but those A1 and A2 are not small.
That's okay. You're right. In this case, this is not small. We do have a bunch of examples of so the standard of the examples is like a Voigt-Grasco example, make it size large and large. And these are still, the commutator getting small and small. And there is a topological obstacle, is because this the torus, you actually got a torus. Almost committing things in the sequence algebra, you will get a torus in it. But torus have a non-zero border element. This border element hits something non-zero in the Kagan algebra, and that thing cannot be lifted because otherwise the things has to be zero. So this is a necessary condition.
Thanks for the question. Any more questions? Okay, then let's thank the speaker again. Then we can go for A4 for lunch.